Hi, my name is Sarah Masi, and I am presenting my project demonstration for Artificial and Computational Intelligence. Introduction. In this demonstration, I will go through the topics of Q-learning, taxi problem, cart-pole problem, and a comparison between the two. Let us look into RL and Q-learning first. Reinforcement learning refers to an agent making the best decision based on the effect of that action on the environment. It looks for the maximum reward for the current state. Q-learning is a model-free RL algorithm. Here, the agent studies all possible rewards it will receive when a decision is made. In Q-learning, a Q-table is made which contains all rewards received by the agent when an action is taken. An action is taken by exploration or exploitation. To plan an action, the agent first initializes the environment and takes an action based on exploration or exploitation. Once this is done, the results are observed from the action and a Q-table is updated. This is repeated until training is over. There are three important variables in Q-learning that an agent follows when taking an action or judging a reward. These variables are learning rate, discount rate, and exploration rate. Learning rate is the extent to which Q values are updated every iteration. Discount rate decides the priority given to an immediate reward. Exploration rate determines how much to explore an environment if the agent should exploit it instead. Exploration means taking a random risky move, while exploitation would be taking the step that the agent is certain will result in a reward. Taxi problem. In this problem, our agent is a taxi who needs to find the smallest route to pick up a passenger and drop them off at the right location. The environment of the taxi can be interpreted as a parking lot. There are 500 states and 6 actions that taxi can take. This is the mathematical equation used for taxi problem. The Q value of a current state and current action is calculated by adding the learned value and the previous state's Q value. The learned value is found out by adding the rewards of the current state and current action with the rewards considered from the discounted maximum reward from the next state. Let me show you the code used to complete this task. This is my program for taxi problem. I have followed the tutorial given in the task sheet and recreated the steps mentioned in the documentation. So this is my output for rendering the taxi environment. In the documentation, they had mentioned to use taxi v2, but in the new version that is not possible. So I've used v3. Then these are the output, and the state 3 to 8 is printed out. This is how it would look like. So this is the reward state that gets initialized in the beginning of the environment. This is the reward table for state 3 to 8 of this the environment. Then this is solving the taxi problem without reinforcement learning. So we would be taking random steps as mentioned in the sample statement. Here I'm calculating the average timestamps and penalties for each episode. This is done for random policy as well. It's displaying the frames that have been calculated in this step. So now we have implemented the Q learning for taxi problem. We've initialized our Q table. Then this is the training code for taxi problem. We have our constant values for learning rate, discount factor, and exploration rate. They are called in our mathematical equation, and then the values are added in our Q table. Rewards and penalties are given in this statement, and our training finishes here. And this is our resultant Q table. This is the same state after reinforcement learning, and these are the graphs I have calculated through these values by appending the rewards and penalties in a list. And then I have evaluated the agent, and this is the graph after evaluation. Cart pole problem. In this environment, our agent is a cart on which there is a pole attached at a joint. The cart slides on a frictionless surface, and the agent should be able to balance the pole. The cart can only go left and right. There are two main differences between the cart pole and the taxi problem in terms of mathematics. Let us look at the first difference, decaying rates. As mentioned before, learning rate and exploration rate is very important to an agent for its decision-making process. In the cart problem, these values are variable and keep decaying as the episodes go by. The rate is calculated using these equations. The second main difference is that cart pole problem has its values in continuous form. The states are continuous and need to be converted into discrete values. For this, K-bins discretizer is used. It creates a tuple which stores discrete values of pole angle and pole velocity. I have structured my solution for cart pole as such. First, a Q table is created. Then the training begins with the while loop. The agent refers to a policy and then it gets the exploration rate for the current episode. The environment is put through the discretizer to make discrete values. And then the learning rate is referred. After that, a new Q value is calculating using the mathematical equation that we covered in the taxi problem. Finally, the Q table is updated and the next episode starts. Let me demonstrate the code for cart pole. So in this part of the demonstration, I will demonstrate the code for my cart pole. So here I have included all my libraries and imported my gem, cart pole v0. I have initialized my lists, which will later have values for my graph through matplotlib. This is a randomly selecting actions code. So it's when the agent does not use Q-learning. So we are checking how many penalties and rewards it gets. Now we'll look at the Q-learning for cart pole. So I have included the libraries. I have made my environment. And here I have for my Q table, I have initialized my bins, my upper and lower values, and these are my functions. So this function will make the discrete values. This is my policy, which will be to choose the maximum reward value in each state. This function gives out the learned value, and learning rate will give out my learning rate. This is a decaying value, and this is how I am calculating my decaying value. It was a big equation as seen in the slides, and I have simplified it by writing it in 3 different steps. This is the same for exploration rate, and this is the calculation for the decaying exploration rate. So in this part of the code, I am training the agent, initialized all my lists, my total values that will also be useful in getting the average values later. So number of episodes here is 1000. Now I'm not going to train it right now, otherwise it will take too long, but I have trained it before, and these were my results and my Q table. So this is the graph I have got from training the agent for 1000 episodes. So this is the pole angle and the episodes, and basically the graph says that initially the agent was not able to balance the pole, but as the episodes have gone by, it has slowly been able to balance the pole and keep it within a certain angle for our problem. And this is the position of the card, and Looking at the graph, we can see that the agent has mostly gone towards the left, but previously when I had trained this agent, at that time it has chosen to go towards the right as well, so this graph has differed before. So this code evaluates the agent. So as usual, my lists are initialized for the graphs, and it will be evaluating for 100 episodes. Here's my while loop. It will send the action to the table and make sure it sends discrete values to the state. It is similar to the taxi problem, but the main difference is the discrete values of the states. These are the Q values that I have received from evaluating the agent, and this is the cart pole pole angle with the number of episodes. So this is also it's quite favorable as it is within the range that we want. So this is my solution for cart pole. So these are the graphs for when the cart pole was trained for like 10,000 episodes. That had gone for a long time, and these are the graphs that had emerged. So the position of the cart has varied quite a bit, and this is the pole angle. So the comparison between the two problems are stated in this table. So the taxi problem has discrete states and the cart pole has continuous state values. And the taxi problem has 6 actions, whereas the cart pole only has 2 actions, that is to go left and right. In taxi problem, our program terminates after a successful drop-off. However, in cart pole, it terminates after 200 steps without failing. In taxi, we get a reward for the right action taken, but in cart pole, one reward is given for one time step. So that's why the graph for a cart pole problem, the reward graph, will be a straight line, whereas taxi can be a little different. And the taxi problem, so it has a constant learning rate and an exploration rate, but in cart pole there is a decaying learning rate and a decaying exploration rate. So that's the main differences. So that's my demonstration. Thank you.